Today we're going to be talking about section 2.9 from the textbook. This is a section on dimension and rank, so feel free to follow along in the textbook, or as with before, I'll be posting this PDF on Brightspace if you would like to follow along there. So recall in the last video, we talked about a basis. So what was a basis? A basis was a set of vectors that had two properties. One, they were going to span our subspace, and two, they were going to be linearly independent. And those were the two properties of a basis. So these were our building blocks for our space. So today we're going to be spending time talking a bit more about bases and what we can do with them. So let's start with our first definition is if we let B be a basis for our subspace H, then for any x in H, we can find coordinates relative to that basis. And these are the weights if we write x as a linear combination of our basis vectors. So if we think of our basis vectors as our basic building blocks for our space, then our coordinates are just saying how much of each of those building blocks do I need to make x. And I can write those coordinates in a vector form, and this is the coordinate vector of x. Notice that I have this little subscript b here. This is telling me, in particular, these coordinates are relative to the basis b. We actually use coordinates like this all the time. So, for instance, if we think about our normal coordinate system, what we're actually saying is these are the coordinates for a vector with respect to our standard basis. So our standard basis vectors are those E1, E2, and so on that we've been looking at all the time. So let's say we have a vector that is maybe has coordinates 2, 3. This would say our x coordinate is 2, our y coordinate is 3. But what we're really saying is that we're taking two copies of E1, which is 1, 0, and we're adding to that 3 copies of E2, or 0, 1. So these are our weights. In this case, this would be sort of our C1 and I guess C2 here. These would be our weights, C1 and C2, where our basis vectors were just those standard bases. So we've actually used this coordinate system before. So let's take a look at how we find a coordinate with respect to a basis that isn't the standard basis. So this is an example of problem 6 from your textbook, section 2.9. And our question is here, we've given ourselves bases, or a basis. In particular, this basis has two vectors, b1 and b2. And this is a basis for some subspace H. And our question is, here's the vector x. Is this vector in H? And if it is, what is its coordinates? So right now, x has 3 entries in its column vector. Those 3 entries are the coordinates with respect to our standard basis, E1, E2, and E3. And our question is, what would be the coordinates with respect to our new basis B? So let's tackle our first question first. Is x even in this subspace? Well, how do we know? How do we know if x is in the subspace H? Well, if B is a basis for H, what we're really asking is x a linear combination of those basis vectors? So is x in the span of those basis vectors? Well, how do we know that? X is in the span of the basis vectors if our system is consistent. So how do we figure out if our system is consistent? We go ahead and put it in an augmented matrix and put it into reduced echelon form. So that's what I've done down here for you in the blue. Is the system consistent? It is, right? This system is consistent, so this is consistent. And so what does that mean? That means that our vector x is, in fact, in H. So our second question, now that we've decided it's in H, is what are its coordinates with respect to our basis? Well, when we're asking what are its coordinates, what we're really asking is, if we write this as a linear combination, what are these weights C1 and C2 for the basis vectors? Well, that's what we found right here. That's what this is. That's telling us those weights. So in this case, C1 is -5/2 and C2 is 1/2. So if we write x, our vector x with respect to this basis b, then those coordinates would be -5/2 and 1/2. Now you'll notice that x started out a three-dimensional vector, but when we write it in these coordinates with respect to b, it looks like it's two-dimensional. Why is that? Well, what we're really saying is, since x lives in H, if x can be thought of as two-dimensional, what that means is that H is a two-dimensional subspace within our three-dimensional space. So since x lives in this two-dimensional subspace, I can write it as a two-dimensional vector. And this sort of leads us to our notion of dimensionality with respect to subspaces. So the dimension of a subspace is just going to be the number of vectors in a basis of H. And this is true for everything except for the zero subspace. So the zero subspace is the subspace that just has the origin in it. And technically that has one basis vector, namely the zero vector, but we're going to say that the dimension of that is 0. So in general, the dimension of any subspace is just going to be the number of basis vectors. So let's revisit this problem that we did in the last video. So this is problem 24 from section 2.8. And what we did in this problem is we said, here's our matrix A, and we wanted to know what's the null space of A. So what is the set of all solutions to the homogeneous system? So we went ahead and we put it in an augmented matrix. We put it in reducer echelon form, and then in the green, we solved for x1, x2, x3, and x4, and then wrote this in parametric vector form. So in this red box here, this is what the null space of A looks like. And we pointed out that we have these two vectors u and v, and those vectors form a basis for the null space. So this is a review from last time. So here's our basis, u and v. So what is the dimension for this basis? The dimension for the null space. The dimension for the null space is just the number of vectors in the basis, which is 2. Notice that each of these basis vectors corresponds to a free variable. And this is always true. When we're writing in parametric vector form, every or at least when we're writing a homogeneous system in parametric vector form, every vector is corresponding to a free variable. And so if we're looking at the dimension of the null space in general, this is going to just equal to the number of free variables in our system. So however many free variables we have, that's going to be the dimension of our null space. Okay, so we just talked about the dimension of the null space. Our other subspace that we were focusing on last time was the column space. So let's talk about the dimension of the column space. The dimension of the column space has a special name. It's called the rank. The rank is just the dimension of the column space. So it's the dimension of the space that those columns span. In particular, if you'll recall from last time, the basis of a column space was simply the columns that were pivot positions, or that had pivot positions. In particular, which columns have pivot positions? They're the ones that aren't free variables. So the rank, or the dimension of the column space of A, the rank of A, is going to be the number of, I don't know how to say this, I guess the number of not free variables. So let's sort of bring this together with what we just talked about for the null space. So the dimension of the null space was the number of free variables, and the rank is the number of not free variables. So every variable is either a free variable or a not free variable. So if A has n columns, it gets brought together in something called the rank theorem. If A has n columns, every single one of those columns is either going to contribute to the rank of A if it's not a free variable, or it's going to contribute to the dimension of the null space if it is a free variable. So if we add those together, if we add together the rank of A plus the null space, the dimension of the null space of A, then what should we get? Well, we should get n, right? Every single one of those n columns either contributes to the rank or to the null space. Okay, before we get to this last theorem on this page, what I want to do is a quick recap of the invertible matrix theorem. So the invertible matrix theorem is what we talked about before break. This was this big long theorem where we had A through L as properties and all of those were equivalent to each other. This was on page 114 of your textbook, section 2.3. So if A had columns that were linearly independent, this is property E, then that meant we were row equivalent to the identity, right? So if all of our columns were linearly independent, then we were row equivalent to the identity, which meant that the columns also span Rn. So if we have n vectors that are linearly independent, property E, that means that those vectors also span Rn, property H. What this means is if I have any, let's say, p columns, those p, or if I have any p columns that are linearly independent, those p columns also span Rp, right? So any p-dimensional subspace is going to be spanned by p vectors that are linearly independent. What this means is that if I have p vectors that are linearly independent, this is called the basis theorem. Let's say H is a p-dimensional subspace. If I have any p vectors that are linearly independent, and all of those live in H, then that means they also have to span H by the invertible matrix theorem. But if they're linearly independent and they span, then they're a basis. Similarly, any set of p vectors that span H are also going to be linearly independent by the invertible matrix theorem. And those are also going to be forming a basis for H. This is because we have p vectors in a p-dimensional space. If the dimension of our space and the number of our vectors don't match, this doesn't hold anymore. But if we have a p-dimensional space with p vectors in it, and those vectors are linearly independent, then they will span, and if they span, then they'll be linearly independent. In either way, they form a basis. All right, we're going to finish up by going back to this invertible matrix theorem. So the invertible matrix theorem, like we said, it has so very many properties, and we're going to add a bunch more today. So we start off by saying if A is an n by n matrix, then the following properties are all equivalent. So if A is invertible, then it's row equivalent to the identity matrix, and there's a bunch more things. The columns are linearly independent, a bunch more things. The columns span Rn. So I reproduced some of them here, and you can find the rest of them on page 114. In particular, let's add in the new stuff. So for property M, what happens if we have columns that are linearly independent and they span? That's the same thing as saying we have a basis, right? A basis is just a set that's linearly independent and span. So that means that the columns of A form a basis of Rn. So let's talk about some of the subspaces we've talked about thus far. For instance, if we're looking at the column space of A, if I'm looking at the column space of A, by definition, that's just the space that's spanned by the columns. Well, what's the space that's spanned by the columns? By property H, this is just Rn. So the column space of A is Rn. If the column space of A is Rn, then what is the dimension of the column space? Well, what's the dimension of Rn? The dimension of Rn is just n, and the column space is that, so the dimension of our column space is also going to be n. We can also ask ourselves, and this is a little bit silly, but we're going to do it anyway, we can ask ourselves what's the rank of A. By definition, the rank is the dimension of the column space, so that's also n. This is a bit redundant, but we're going to put it in there anyway. If the rank of A is n, and the rank of A plus the dimension of the null space is the number of columns, then what should the dimension of our null space be? Well, if we're looking at the dimension of our null space, if that plus the rank has to equal n, and the rank already is n, then this dimension has to be 0. And so if this dimension is 0, then what actually is the null space itself? The null space is going to just be the 0 subspace. This isn't that surprising, right? If our columns are linearly independent, then that means we only have the trivial solution to the homogeneous system. And the null space is asking, what are the set of solutions? Well, it's only the trivial one. It's only the 0 vector. So we have now finished off another 6 items in our list. And we'll keep adding more throughout the semester. So I hope that was helpful. I will be posting another video soon, and in the meantime, feel free to email me with any questions you may have or sign up for my virtual office hours.